Greetings all, F-Man here. Welcome back to Flight Simulator 2020 and welcome to the Boeing 737-800. Earlier today we had an incident involving the hull loss of a 737-800 Jeju Air Flight 2216 attempting to land in South Korea, 181 souls aboard. As far as I am aware at this point, 2 survivors. Video of this airplane on approach and landing in an attempted belly landing appears to show that we've got no landing gear deployed, no flaps, no slats, and no spoilers deployed. Well, what could possibly contribute to that condition occurring here on a 737-800? Let's take a look at the electrical and hydraulic systems here on the 737-800 in Flight Simulator via PMDG and see what is going on. As we're in the cockpit here, we can see that the airplane is in a configuration that we would describe as cold and dark. We've got no power applied to the airplane. None of our cockpit systems are operating. None of the flight control systems are in operation at this point. This means that we've got ourselves no capability to control this airplane beyond the cable mechanical control surfaces that are active on this airplane, with no hydraulic booster pumps or anything like that. So flight control would be very, very slow and sluggish to respond, and it would require a great deal of physical effort from the crew in the pilot and first officer seats here. However, to rectify that situation, we've got ourselves the ability to bring electrical power into the airplane. We have got 3 primary means of generating electrical power and thereby hydraulic pressure on the airplane. The ancillary control surfaces on the 738 are the flaps, slats, and spoilers. They are actuated by hydraulic pressure. Hydraulic pressure is activated and generated by electrical and engine-driven pumps. Power for those systems is generated by the 2 main engines, the engines that are mounted on the other sides of the wings. As you can see here, we've got obviously a left engine and a right engine, as well as a third engine called the auxiliary power unit. You can see the exhaust ports for the auxiliary power unit here in the tail cone of the aircraft. The auxiliary power unit is also a jet engine. It's a gas turbine engine. However, it's generating a very negligible amount of thrust in terms of flight control, but it's a jet engine running off the same fuel system as the rest of the airplane in terms of the 2 main engines used for thrust generation in flight. However, that engine is very important for generating hydraulic pressure as well as electrical power, as we will find out. However, if we're going to turn this airplane on, we will first turn on battery power on the DC bus. So we turn on DC power, and you see that we have got our overhead panel come on in terms of things that are not operable at the moment because we don't have enough power to operate these systems. You'll see as well our main status board here in terms of things that are running or not running in terms of flight controls and information that we will need to fly the aircraft. So that's all very good. You'll also see here we have got our engine control pedestal here, the center pedestal between the 2 pilot seats. We've got our thrust levers, we have our thrust reverse levers, and we've got on the left-hand side the speed brake control lever and our flap control lever. First thing we need to do, because we're on battery power here, and we may get caution warning here to show that we are discharging our DC bus, DC obviously coming from battery power, we will need to operate the auxiliary power unit. We'll see here this gauge here, roughly center of screen. That is showing exhaust gas temperature from that gas turbine engine mounted in the tail that we took a look at the exhaust ports of earlier. That's the auxiliary power unit, and it will generate hydraulic pressure and electrical power for the aircraft. Bring it to the on detent here on the start switch, and then we will start the auxiliary power unit. So the auxiliary power unit has now been told to start. We're going to get a caution warning for low oil pressure in a moment. There that is. And we'll see the exhaust gas temperature rise. Once the exhaust gas temperature rises, that tells us that we have shaft RPM on the APU as well as fuel flow and an attempt to ignite that fuel. It'll peak at about 700, 800 degrees C on the EGT, and then it will slowly ramp back down. We'll expect things to stabilize at around 400 degrees C on the EGT. We'll also expect here to see in the center of this bus transfer panel, we'll expect to see APU gen off bus, and there it is. We can bring the APU gen online. And now the airplane's electrical system is running off of the auxiliary power unit, which is really good. So, the APU allows us, first of all, to charge our battery, so the DC bus now effectively doesn't matter. See that there with our buses showing the power coming in. It also allows us to do a couple of things in terms of generating hydraulic pressure as well as to operate the pneumatic system on this airplane. Pneumatics on an airliner are really important because it allows you to have climate control as well as pressurization. Obviously, when an airplane flies at high altitude, the ambient atmospheric pressure will drop, and above 10,000 feet, it starts to drop below levels at which normal human function can be withstood. Therefore, we have pressurization on airplanes, and this is something that started to come along during the Second World War as bombers in particular started to fly higher. And the crew started to report the effects of hypoxia. So we've got ourselves a pressurization system on all modern airliners, allowing us to operate at altitudes well above 10,000 feet. So what we've got here are the bleed valves. These are valves that enable us to take air out of the engines or the auxiliary power unit to enable us to fly at altitudes above 10,000 feet. What we've got here in the center switch here, this is for the APU bleed valve. This takes air out of the auxiliary power unit and allows us to charge the system to pressurize the cabin. We'll do that. You'll see our pressure rise here on the duct pressure. So we have got air now to charge the pressurization system. If we open up our packs and our outflow valves from the APU, yep, you hear our valves open and you start to hear airflow from our APU. So now we have climate control in the airplane, enabling us to pressurize this cabin to an altitude of around 10,000 feet or so above ground level barometric. That's cool. What we will also have is the ability to generate electrical power, quite obviously, but also the ability to generate hydraulic pressure. Right now we have no hydraulic pressure on the airplane, which means that no matter what I do with my spoilers are now in the full ground deploy detent. We go out here on the upper surface of the wings. You'll see the spoilers are here, roughly center of screen. They are retracted. They're not deployed. The spoilers come out either in flight, in the in-flight detent, in order to bleed off speed in flight, or when the airplane touches down with the main landing gear. Those are the two wheels that are just aft the center line on the longitudinal axis of the fuselage. The main gear come down first. They have what are called weight on wheel switches, which will tell the airplane's onboard control systems that we have weight on the wheels. The airplane has touched down on the ground, and they will deploy the ground spoilers, which are the outboard most panel here, in terms of allowing the spoilers to come up and spoil lift on the wings. This keeps the airplane from bouncing after initial touchdown and enables the airplane to lose speed after touchdown. Very important. They will also be operated in conjunction with thrust reversers. The thrust reversers are on at least the 737-800 panels that come out from the after portion of the main engine nacelles. You can see that we have got this very conspicuous shut line on the main engines. This will brake rearward, and the after portion of the nacelle will transit rearward longitudinally, allowing the engine thrust to be redirected from the aft portion of the engine here. You can see the core of the engine as well as the bypass portion of the engine thrusting aft to allow forward movement. This will redirect a lot of that airflow forward and down, allowing the engine thrust to start to affect deceleration of the aircraft. And again, that's something that is enabled only on the ground. Those thrust reversers obviously are actuated via hydraulic pressure. Without any hydraulic pressure on the airplane, though, I can deploy our spoilers, flight and ground spoilers, as well as deploy our flaps down to 40 degrees, which is their maximum extension here on the 738. We have leading edge slats, which are protrusions that come out from the leading edges of the wings, as well as the trailing edge flaps, which will extend from the trailing edges of the wings. Nothing is happening here on the wing surface because we have no hydraulic pressure. These are hydraulically actuated surfaces. However, once I turn on our electrically driven hydraulic pumps, go back outside, you will see that we have got the spoilers extended, the leading edge slats are extending, as well as are the trailing edge flaps. That's able to occur because we have the auxiliary power unit in operation, as well as our electrical buses for the hydraulic system on. The overall function of the leading edge slats as well as the trailing edge flaps is so that we can have speed reduction in flight. In other words, as we extend these lift generating surfaces on the forward edge of the wing as well as on the trailing edge of the wing, we change the chord of the wing, which means that the wing can generate more lift at lower speeds. Those lower speeds enable us to achieve lower speeds so that we can land at more reasonable speeds. If we don't have extension of the leading or trailing edge flaps and slats, we will have higher speeds required upon landing, which is going obviously to increase our required landing distance. On the video that has come out of Jeju Air Flight 2216, we do not see evidently the extension of the leading or trailing edge flaps and slats, which means that the airplane is going to have to maintain higher speeds in order to maintain flight. This is also going to necessarily require a higher landing speed, which is something that we also see. Once the airplane in the incident video, as is evident, once the airplane touches down, we see the impact of a retaining wall off of the runway threshold on the opposite end, probably at a speed in excess of 100 knots. And that, in part, is due to the apparent inability of the crew to extend the landing gear as well as leading edge slats, trailing edge flaps, and spoilers, which of course are all hydraulic systems. However, here with the APU running and our electric hydraulic pumps actuated here on the hydraulic bus, we can say that we have got hydraulic pressure sufficient to actuate the flap slats and spoilers as we have just demonstrated. Let's shut the spoilers now. Back into the flight detent, which means no spoilers are deployed. And in addition to that, we have our flaps at 40 degrees. We can also retract the flaps if we want, bring them back to the completely retracted detent at 0 degrees. And you'll see that here on our indicator as it starts to scroll back up from 40 to the up position. You'll hear the hydraulic motors running here. So when you have hydraulic pressure on the aircraft, it means that you have the full ability to actuate the slats, flaps, and spoilers as you would need for a nominal landing configuration with or without the landing gear. As the flaps come up, we also have our pneumatic system running. The APU obviously providing pressurization and climate control for the passenger cabin as well as the cockpit. In addition to that, because we have the APU running and we have the pneumatics running, we can also run the engine start valves, which will enable us to start the engines. The engines, the main engines there under the wings, are obviously the primary sources for electrical power, hydraulic pressure, and pneumatics when the aircraft is in normal operation in flight. Obviously, the engines providing the power to get us off the ground in the first place. So what we will do, we can shut our packs down. And then, with our engine start panel here, we can select the right engine in terms of the ignition, and then we can select the ground start. And we will start to see, once we have our start valve open, we have a low oil pressure indicator there. Nothing has happened, because we've got to shut down our duct off at the APU. We start to have shaft RPM now once we have the pneumatic system configured correctly. So the APU bleed is open. And we've got our crossfeed valve set to auto. Once we have 20% N2 as we have, we can open our fuel valve. And we'll see fuel flow there on engine number 2. And we have a light off at engine number 2. So once we've got the engine running, fuel flow confirmed, and the exhaust gas temperature is rising, we can shut down our start valve and ignition switch. That will also happen automatically at about 60% N2. And the engine is running. Once we have about 60% N2, the engine will start to become available on the main bus to provide electrical power. So Gen 2, runoff of engine 2 is now available. Gen 2 is now on the bus. We can shut down the APU bus. And now the airplane is running off of engine number 2. If we want, we can shut down the electrical hydraulic pumps and start up the engine-driven hydraulic pumps on bus B. And that will also provide pressure ample enough to run our slats, flaps, and spoilers. So we got our spoilers deployed. I'll select flaps 40. We'll go back outside. Now this is just with one engine running. And you'll see that we have got our spoilers deployed. We've got ourselves the leading edge slats extending, and we have got our trailing edge flaps deploying as well. This is just one hydraulic pump running off of our right-hand engine. There we go. You can hear the drive motors running, the jack screws that are operating the flaps and slats. They have stopped. If we go back into the cockpit, you will see that we have got 40 degrees indicated on flap deployment, leading as flaps extended. There's just one engine running with no electrical hydraulic systems selected on the bus. So we have one engine running. The APU is offline. The APU is running, but it's not on the bus, either electrically or hydraulically, and we have enough hydraulic pressure to actuate the flaps, slats, and spoilers. We don't see flaps, slats, or spoilers deployed on the accident video here on Jeju Air Flight 2216. That indicates to me a complete hydraulic system failure. Similarly, we do not see symmetrical thrust reverse deployment on Jeju Air Flight 2216. The thrust reversers, as we talked about earlier, are the panels of the engine nacelles aft that will deploy rearward longitudinally when the weight on wheel sensors detect that the airplane has touched down on the runway in the main gear, and then they will redirect the engine thrust down and forward. We do not see that symmetrically. We see that on the right-hand engine, engine number 2. We do not see that on engine number 1 on the left-hand side of the aircraft, which tells me that we may have had a complete hydraulic failure either because of partial hydraulic pressure existing, allowing for the thrust reverser deployment on engine number 2 prior to the complete loss of pressure, or the aerodynamic effects on the potentially failed engine number 2 have opened up the thrust reverser duct on engine number 2. We don't really know at this point. Thankfully, however morbidly, what has apparently occurred here in the wreckage is that the flight deck and cockpit area has survived more or less intact on the accident aircraft, which will allow us to see things like switch positions. So that may be an area of interest on the investigation. Regardless, if we want to start the number 1, the left-hand engine, similar process here. Ignition selected to the left. Engine start valve open on the ground detent. We see start valve open here, and we see N2 RPM start. Once again, we get to 20% N1, and then we will open the fuel valve. There's 20%, fuel valve open. We'll wait to see fuel flow. There it is. We hear the light off. EGT is rising. We'll shut down the start valve and the ignition switch, and the engine will spool up. Again, once we get to about 60% N1, or N2 rather, we will start to see the engine become available on the generator bus. So both engines are running. They're more or less stabilized. Engine number 1 is now available. Engine number 1 is on the bus. You will see we can start the engine 1 hydraulic pump, and pressure is now, the low pressure warning light is off. And if we turn on the electrical pumps, you will see that the warning lights also turn off for those. We can also turn on the packs, shut off the APU bleed, turn on the engine bleeds, and we have ourselves full pneumatic system availability from both engines. If we want, we can shut down the APU completely, which we have now done. Turn on our fuel pumps. These are electrical pumps. And the airplane is now running completely off of the power of both engines. We have the ability to run the entire hydraulic system, the pneumatic system, and the electrical system from the engines themselves. So we have booster pumps that are augmenting the cable-linked flight controls, as we would expect, as well as the full ability to extend and retract the ancillary control surfaces, flaps, slats, and spoilers. Obviously, spoilers are now retracted, and we've selected flaps up. And you see the trailing edge flaps retracting in accordance. So there you go. Engines are running, flaps and slats are up, spoilers are retracted, the wings are now in what we would call a clean configuration. And this is pretty much matching what we see on the accident video. So what this tells me is that this airplane had very little, if any, hydraulic pressure available at the time of its attempted belly landing. Obviously, we don't have ourselves any landing gear deployment. The landing gear doors are not open. On the 737, it's actually somewhat interesting because we don't have landing gear doors. We have the main gear, which just fold up into the fuselage. The nose gear does have doors, but the main gear do not have any doors because the airplane sits rather low on the ground. But we don't have the landing gear's doors open on the nose gear. We don't have any evidence that the landing gear has attempted to deploy either via hydraulic or gravity actuation, which is the reserve emergency means by which to deploy the landing gear. So that tells me that the pilots were dealing with a complete hydraulic failure. They had no ability to control those ancillary control surfaces. They had no ability to deploy the landing gear, and they needed to get on the ground immediately. Unfortunately, for the people on Flight 2216 of Jeju Air, it was not enough. It was too late. The pilots touched down on the runway on their belly. About halfway down the runway, the airplane overran the runway and then impacted a retaining wall off of the runway threshold, upon which it underwent total structural breakup and caught fire. Again, as far as I'm aware, we have 2 survivors confirmed. Don't know if anybody else is confirmed to have survived at this point. However, obviously mass casualty incident here in South Korea earlier this morning. And it's going to be the object of some obsessive investigation work because quite obviously the airplane did not have the required control available to try and slow itself down prior to its attempted belly landing. And that's something that will be of interest to the investigators as we go here through our power down, we've got the APU back started and it's on the electrical bus. We've shut down the main engines. Main engines obviously are shut down, so they're no longer providing electrical power or hydraulic pressure. And then beyond that, we have our APU running the hydraulic and electrical systems. Shut down our fuel pumps. Caution and warning lights obviously coming on for those. Bring our APU bleed valve back online. So the pneumatics are back up on the APU. However, we can shut that down. Battery is up, being charged by the APU. Previously it was being charged by the engines. Then the APU offline, running off of battery power. Shut the APU down, so now the APU isn't even running. Once the APU shuts down, which again will be evidenced by the drop in exhaust gas temperature on this gauge, we will have no ability to generate hydraulic pressure or pneumatics, or really any usable degree of electrical power beyond just being able to start the APU. Again, expecting a caution and warning just to tell us that we are discharging on the DC bus. Just waiting on the EGT to drop on the APU. All right, EGT is dropping, APU is off. We can shut the battery off. There we go, airplane is off. Once again, back to the cold and dark configuration. So what this tells us is that, unfortunately, Jeju Air Flight 2216 apparently had a complete loss of hydraulic pressure, meaning that they had no ability to use their ancillary control surfaces, flap slats, and spoilers, which severely limited their ability to slow down prior to landing, which unfortunately contributed to their overrun of the runway into belly landing, ultimately resulting in their impact of a retaining wall outside of the runway threshold and subsequent structural breakup and fire engulfing the aircraft, and unfortunately resulting in the mass casualty event that we have evidently observed. Until next time, F-Band saying thank you very much for watching, and of course, we will see you soon.